Welcome back to multivariate calculus. In this video, as it says above me, we're going to be looking at first-degree equations. You should already be incredibly familiar with first-degree equations in two variables. These are the equations of lines that you learned about when you first started studying graphing in an elementary algebra course. More recently, the bulk of the introduction of calculus was a series of tools that would allow you to take more complicated functions and pretend that they are lines at least in a narrow window so that you can use the tools that you have for working with lines to work with more complicated functions. And so for that reason, it makes a nice warm-up, a nice place to start as we start thinking about how to get into things that are more than two-dimensional. So without further ado, I'm going to go ahead and get my head out of the way. And let's jump right in to the coordinate plane. Again, you should be familiar with all of the concepts here. But if you are anything like I was when I was a student, the concepts all make perfect sense, and the vocabulary, you never really worried about. In order to extend these ideas, we're going to make a little bit more use of the vocabulary than you might have otherwise. So I want to make sure that we have all of that down sanely. There are actually a couple of different ways that you can assign coordinates on the coordinate plane. The one that you're most likely the most familiar with is called the rectangular coordinate system, or sometimes the Cartesian coordinate system, named after the French philosopher René Descartes of I think, therefore I am fame. But the coordinate plane has a horizontal axis, which we normally label as the x-axis, a vertical axis we normally label as the y-axis, and it divides the space into four regions, which we call the quadrants, and we normally name using Roman numerals, 1, 2, 3, 4, proceeding counterclockwise. All right, counterclockwise is sometimes also called a right-handed orientation, because if you take your right hand and you place your right hand with your thumb facing up on the coordinate plane and then curl your fingers. Let's see if I can actually get that to look like it works here. Curl your fingers. Your fingers curl from the first quadrant to the second, to the third, and then around to the fourth. It's a little bit too far away for my camera to really understand where I am there, but you get the idea. So that's what we mean when we say a right-handed orientation. And of course, we can take our ordered pairs x, y, we can plot them on the coordinate axis, and that forms a graph. All right, so a graph, the easiest way of defining it is literally the solution set of an equation in two variables, or as we'll see as we go through this course, in 3 variables or 4 variables or 27 variables. A first order equation in two variables is any equation which can be written in the form ax plus by equals c, and the graph of a first order equation forms a straight line. In the rectangular coordinate plane. As I mentioned, there are other coordinate systems other than just rectangular, so we have to specify that in the rectangular coordinate plane, um, every first order equation has a graph which is a straight line, and every straight line has a representation which is a first order equation. Um, if you have not previously, feel free to contact me about why that's the case. There's a really interesting proof. It's a little bit beyond the scope of this course to get into, but you can actually verify using an axiomatic definition of a straight line as the shortest path connecting two points that this actually does give you the line that we want. In analytic geometry, we actually go the other direction. This is the definition of a line, and then we can prove some properties like it is the shortest path connecting two points and all the other things. Right. You've spent a lot of time graphing equations of lines. I don't expect that this is going to be particularly challenging to you. But I want to specifically look at lines which pass through the origin. Turns out when you have a line that passes through the origin, there are a couple of other really nice properties that you can look at that you can also look at for other lines, but it's just a lot easier. So let's graph 2x plus 3y equals 0. There are several different ways you can choose to go about this. I'm going to take the simple approach of plotting some points. If I plug in x equals -2, I get that y is 4/3. If I plug in that x is -1, I get that y is 2/3, 0, -2/3, and -4/3. So with just that information, I can start plotting some points. And then playing a simple game of connect the dots, we have a nice graph of a line. Right. And again, I am looking right now specifically at lines which pass through the origin. It makes life a little bit easier. These ideas can extend to any kind of line, but if we stick with things that pass through the origin, we don't have to worry about getting into the details of the definitions for something that's not really all that important compared to what we're really trying to do here. All right. Of course, you're familiar with the slope of a line. There are several ways you can calculate slope. My favorite is to rearrange the equation to be in slope-intercept form and then read the slope right off of the equation like that. The slope of this line is -2/3. What you may not be as familiar with is the angle of inclination of a line, which is actually a fairly straightforward concept. The angle of inclination of a line is defined as the angle formed between that line and the positive x-axis. When you are looking at a line that has a positive slope, this is a really easy thing to measure. When you have something like this with a negative slope, there are two competing schools of thought. Some people like to have the angle of inclination be somewhere between 0 and pi, 0 and 180 degrees. Other people like to go between negative 90 and positive 90, or negative pi over 2 and positive pi over 2 in radians. That's actually the track I'm going to take. So the angle of inclination is going to be the angle this way. It is going clockwise, so it is going to be a negative angle. And we define the tangent of that angle is simply the slope of the line. So in this case, our angle is the arctangent of negative 2/3. And for my purposes, that's good enough because that's not an angle I know exactly, but I know exactly that it is the arctangent of negative 2/3, so I'll leave it there. If I had to do more work with this, if this was an application problem where I was trying to do some calculations from here, I would grab a calculator, plug that in, see what happened. You're welcome to do that. You get a value that's something like negative 0.59 radians, but that doesn't really mean anything to me. It probably doesn't mean much of anything to you, which is why I'm just as happy to leave it as arctangent of negative 2/3. The other thing that you have done previously working with lines is to write the equation of a line using point slope form or something related to it. Something like y minus y naught is m times the quantity x minus x naught. Some people use slightly different variables, but it all works out the same. This is the line that goes through the point x naught, y naught, and has slope m. And so if you have a point, and you have a slope, it's simply a plug and chug game. So in this case, to write the equation of the line through 1, -4 with slope 3, it's going to be y minus -4 is equal to 3 times the quantity x minus 1. Rearranging just a little bit. And traditionally, we write our lines in slope-intercept form because that is a uniquely defined way of writing a line. Right? There is exactly one way to write the equation of a line in slope-intercept form. There are infinitely many ways to write it in standard form or in point-slope form. The interesting questions come up when the slope is a little bit harder to come across. You can define the inclination of a line instead of the slope. And if you do that, then you have to go through an extra step. use the inclination to calculate the slope, and then once you know the slope, you can go ahead. You can have an equation that is 2 points, calculate the slope of the line passing through those 2 points, and that's the slope of your line. Then take one of those points as the point your line goes through. It will naturally go through the other point, but you only need one for the equation. And then, of course, the most interesting thing that you spent time with in calculus prior to this is using the tangent line approximation. Let's do this in a different color. Let me get my head back out of the way. So for example, if I want to write the equation of the line, which is tangent to the curve, x squared plus x minus 6, at the point x equals 1. This is a task that is very common in a calculus of a single variable course. The first thing we want to do is evaluate. Y of 1 is going to be 1 squared plus 1 minus 6, which comes out as negative 4. And then we need to take the derivative. Y prime of x is going to be 2x plus 1 minus 0. And we evaluate the derivative at the point we care about, which in this case comes out as 3. So because we evaluate y of 1, we get negative 4. That means we're going through the point 1, negative 4. And because our slope came out as, or our derivative evaluated to 3 here, that is our slope, m equals 3. And hey, that's a problem we just did, right? The equation of the line that passes through 1, negative 4 and has a slope of 3. I don't even have to think about that. I just look at the last problem we finished and write that solution down again. Something a little bit more cumbersome helps if I write down the whole problem. Write the equation of the line, which is tangent to the curve x squared plus 2y squared equals 6 at the point 2, 1. All right, first thing, this particular equation is going to be the equation of an ellipse. It's a second degree equation in 2 variables, which we'll be talking about a little bit later in this lesson. But we have here an equation in 2 variables, which is not a function, not solved for y, so to differentiate is a little bit more challenging. My favorite tool here is to differentiate implicitly. Assume that y is a function of x, and sometimes I write that out. Oops, let's use the thinner pen. To remind myself what I'm trying to do. right? Assume that y is a function of x squared plus 2 times y of x squared equals 6. And then when we differentiate, the derivative of x squared is 2x. The derivative of 2y squared is going to be 4 times y, but then you have to multiply by the derivative of the argument, right? This is a function of a function. We're taking the function y of x and squaring it. So we have to use the chain rule here, and we'll get 4 times y prime. And then on the right-hand side, the derivative of 6 is 0. So doing some rearranging on this equation, we get that y prime is negative 2x over 4y. And yeah, I could reduce that, but I'm just going to plug this value in and deal with it from there. Negative 2 times 2. Right, so y prime at 2, 1 is going to be negative 2 times 2, which is negative 4, over 4 times 1, which is positive 4, and negative 4 divided by 4 is negative 1. So that's my slope. Right? This problem simplifies to become write the equation of the line through the point 2, 1 with slope negative 1. And that's a fairly straightforward process. Y minus our y value, which is 1, is equal to our slope negative 1 times the quantity x minus our x value, which is 2. So y minus 1 is negative x plus 2, which means that y itself is the opposite of x plus 3. All right, that's the basic idea of equations in one variable, or I'm sorry, first degree equations in 2 variables. Get what I'm talking about. Before I wrap up, here is a problem for you to try. Write the equation of the line through the origin with, that word is supposed to be inclination. I apologize, my writing is terrible enough, and then this touch screen is not quite calibrated correctly, making it even worse. Write the equation of the line through the origin with inclination angle theta equals pi over 4. Right, that's not a line that I had written so far, but I've given you all the tools that you need to figure that one out. So take some time, write out your solution there, and then once you feel comfortable with that, I'll see you in the next video.